Hi there, and welcome to Lesson 9.1b, where we're going to continue looking at quadratic graphs and their properties. Our goals today is to understand the effects of changing the a and the c in a quadratic equation, and also to solve a real-life problem using a quadratic equation. So in class, we did an investigation where you used graphsketch.com to look at the effects of changing the a and the c in a quadratic equation. You were then asked to fill out the what did you learn part of your notes. So let's take a look and see what you should have learned. So first question says, what happens to the graph when the value of a is made larger than 1? And when you did that, the parabola became more narrow, didn't it? And then the second question asks you, what happens to the graph when the value of a is made in between 0 and 1? So for instance, a fraction like 1/2 or 1/4. And when you did that, you saw that the parabola becomes wider. The third question is explain what makes the graph of a parabola either a smiley face that is open upward or a frowning face that is open downward. And what you came to conclude that is that when you have a smiling face, the a value is positive, and a frown, which is the upside down parabola, that's when the a value is negative. In question number 4, what happens when there's a number added or subtracted to the equation? That's your c value. And what happened there was the parabola moved up or down on the y-axis. It was kind of like it was the y-intercept of the equation, wasn't it? So these are the answers to the questions in the what did you learn section. All right, let's take a look at the application question. Here we have a child drops a pebble from a height of 30 feet above a lake. The function that's given here gives the height of the pebble after t seconds. And we're asked how many seconds does it take for the pebble to hit the water? Notice that this is a quadratic equation. Now let's just take a look at what would happen if we were to graph a situation that looks like this. So we have height as our y, as you can see that the h is in the y location of the function, and we have time in seconds. So notice that I'm counting by ones on the x-axis, but I jump way up to 30 here, and this really isn't drawn to scale. But if I were to drop a pebble 30 feet above a lake, it's going to fall like this. Okay, do you see how this looks like 1/2 of a parabola? And the other half of the parabola would actually be right back here, wouldn't it? Okay, but we don't care about the back side of the parabola. We just care about the front side here. We're looking at the positive numbers. Okay, so this is what would happen if I graphed it. So what I'm looking for is right down here, when it hits the ground, what time is that where it's going to hit the ground? That's what we're looking for. How many seconds is it going to take? All right. So in order to do that, we're going to use what we call a dropped object model, or the function for a dropped object. And this is what it looks like. H is equal to -16 times time squared plus c. The c is our starting height. So you'll notice that in the equation that we're given, this plus 30, right here, that's the starting height. That's 30 feet. So that's why we made this a 30 right here in our equation that's given to us. Now the ending height goes right here. This is our ending height, and we want this to end at a height of 0 when it hits the ground. So we're going to be plugging in 0 for our ending height. We want to know how many seconds does it take to hit the ground, and the height of the ground would be 0. So let's just go ahead and we're going to plug in 0 for height, and we're just going to write the equation -16t squared plus 30. So being that this is a quadratic equation, we have the a value of the equation is -16, the b value is 0, and the c value is 30. Okay, so let's solve it. I'm just going to switch colors on you here. So we've got t that we're solving for time. So we're going to subtract the 30, giving us -30, oops, equals -16 times squared. And then to get the t, we'd want to divide by -16. And then we're going to use our calculator here. So I'm going to type in -30 divided by -16. And I'm not going to round this. I'm going to write exactly 1.875 equals t squared. Now I don't want time squared. I want just time. So I have to do the opposite of the squared, and that would be square root. That's going to cancel that. So it's going to give me time equals, I'm going to take the square root of the other side as well. And so I'm going to type in my calculator square root of 1.875. I'm not rounding anything until the very end here. So I'm going to go out to the one decimal place. So I'm going to approximate this. It says 1.36 on my calculator. So this 6, that 6 is going to bump this up right here to a 4. So I'm going to say this is going to take approximately 1.4 seconds to hit the ground if a pebble gets dropped 30 feet above a lake. It's going to take 1.4 seconds. So you can see my graph here that where it dropped would be about that 1.4 seconds. And that was just a quick sketch of the graph. But that's how you would apply a quadratic equation using the dropped object model. Okay, let's look at a summary here. So the goal of this lesson was to see how does changing the A and C affect a graph of a parabola. And we notice that when we look at the A, if it's positive, it opens upward. If it's negative, it opens downward. Also, if the A value is greater than 1, the graph becomes more narrow. If it's between 0 and 1, it becomes wider. When it comes to the C, by changing the C, you're going to move the parabola up or down along the y-axis. Then we also were looking at the dropped object model too, where we were applying a quadratic equation. Thank you for joining me for lesson 9.1b and have a great day.